All right, let's boogie. Polynomial functions, domain and range, a topic that just keeps coming back. I love talking about it. I think it's important. Now, I am making the assumption that you have watched the power functions video. Now, if you haven't, I guess I'll put up a link up above. You can watch it there, because once you do watch it, then understanding domains and ranges for polynomial functions is actually rather simpler. Now, a polynomial function is just an addition and subtraction of power terms. And that's why the reason for watching those power functions is super useful. And you will find that whenever you do have a polynomial, it's going to be of a certain order or degree. And it turns out that pretty much the highest order is the one that will dominate as the function, okay, and as the input, x becomes larger and larger in magnitude. So here on the screen, what you see is you basically have your input x, and then you have a function, which is f of x, and that will be a polynomial function, which is just right above it. So that's the standard form of a polynomial. And then you have an output, so we'll call that output y, which is basically nothing else but your function output. Now, our interest is in trying to think of, okay, so what is the possible domain, and then what are the resultant ranges for all the polynomials that we could kind of come through. Now, a domain is simply all the allowable inputs into a function. So what inputs? Ideally, we would like to be able to input every single number, so every real number. And then your range is, if you do take your domain and those inputs, what will be the resultant outputs? Okay, so in terms of the output, what can they span? And again, it would be great if they would span the entire real number line, but they don't always do so. And we see that in polynomial functions. There is, however, quite a pattern which emerges from the power functions. So if you recall, and so within these cases and these polynomials, you will have kind of two things happening, okay, with every single polynomial, and the same thing with every single power function. So those two things that will be happening are, you can take and divide every single polynomial into the case when n is basically even, and that n would be the order of your polynomial. So 2, 4, 6, 8, and so on. And then the other case is when n is odd. And odd, so that means it can be 1, 3, 5, and again, so on and so on. Now, if you go back to your power functions, what you found was that we had, for our domain, so in terms of our domain for the power functions, for both, for n is equal to even and n is equal to odd, we found that we can actually input any input we like, which is a real number. And that shouldn't be a surprise, again, because these polynomials are just made up of these power terms that you have, and they just keep going and going. And if you're going to take a power term, well, you can input anything you like. So any real number will work. You're going to get a result back. There are no denominators, so there's nothing for us to worry about in a polynomial function, which is great. So that's the case both for n is even and also for n is odd. So that's something that you can think about in terms of the domain, that it can take in any real number you like. I mean, of course, unless you yourself restrict it to a certain range that you might have, okay, or a certain interval, I should say. Now, for the range, what you're going to run into is, unlike your domain, there is a distinction between the fact of your n being even and then your n being odd. Now, for n is being even, I will kind of do a little bit of a deja vu, right? When you were studying quadratic functions, and those quadratic functions, you found that for those quadratic functions, you either had parabolas that were kind of looking upwards or parabolas that were kind of looking downwards, which meant that you had some kind of a minimum, in this case, when they were looking up, and then you had some kind of a maximum, okay, when you were looking down. And that resulted in the fact that for your range, well, we couldn't have an output which was actually below the minimum when the parabolas were looking up, and that was the case when your A that you had, so in this case it would be A2, that you would have would be positive, so then it would be looking up, and then when your A was negative, your parabolas would start to look downwards, right, for quadratics. So that restricted us to a range. Now, could we possibly extend this restriction so it's almost like we had, so I'm going to call it y, okay, for our output. So our output could be really anything that we want, but we were being restricted, so either y had to be greater or equal to the minimum, or it would be same thing, y would be any real number, so any output that we could obtain, but, you know, we might be restricted that there might be a maximum. And now the question is, well, if you only study quadratics, could you extrapolate all of those results in these ranges to also having that to higher orders? So for example, instead of just quadratic where n is equal to 2, would that work for n is equal to 4 and n is equal to 6 and 8 and so on and so on? And it turns out yes. Now, unfortunately, finding those minimums and maximums isn't as easy when you have a higher order than a quadratic, because quadratic was pretty nice. We could put it in our vertex form and then get the vertex, and we know exactly what the minimum or maximum is. But for polynomials of higher order, it's not always that simple, right? And I'm going to just show you through graphing what can happen. But the nice thing is that the extrapolation from a quadratic continues on. So whenever n is basically even, as we have it in this case, the result is that the domain can be any input that you like, so any real number. But the range is always going to have either some kind of a minimum, right? And then it's going to be anything above that minimum, or it's going to have a maximum, and it's going to be anything below that maximum as well. So that's what you will run into. Now, what about if n is odd? Well, if n is odd, we already said that the domain can be any real number. And indeed, that's the case because, again, it doesn't really matter if n is odd or even. We're just adding and subtracting all of these different power terms that we have. And that's not a problem. And then for your output, however, because you do have n as an odd number, that now allows you to have, and you, if you may recall, a cubic. So if I would take, okay, and my function would have been something like this. Let's say a3 is equal to 1, and then I just have a cubic. You may remember that this kind of looked like that. And we had, okay, both positive numbers that were kind of going upwards. So if we were drawing this out, so, you know, if we had our x and y axes, it kind of looked like this. So they were going upwards in this direction and then downwards in this direction, because if you took negative inputs and you cubed them, right, and they got larger and larger, it would just provide you with an output which was larger and larger negative. So that was different than a quadratic or any polynomial with an even order. So it turns out that for polynomials with an odd order, so 1, 3, like in this case, a cubic, or n is equal to 5 or 7 and so on, they will always, kind of like your power function, be dominated by your highest order, odd order of whatever it might be. And that means that my range for these, well, the nice thing is that we don't have to worry about it much, because your range is going to be actually any real number. And that happens for all the odd powers. So let me show you this. I'm going to show you this through decimals, because I love when students take kind of visual aspects and then be able to see it and then play around. And because now we have these wonderful tools like decimals, we might as well do it. So I have prepared, so here is a function, so a polynomial. You see that on the top left. And then I literally input it in, so you know, a5. So I went as high as as n to the 5. And then I have a4, you know, a3, a2, a1, and so on. Now, just below it, okay, I've added and I basically said that all of those constants are 0 at the moment. So that's why you just see a blue line, which is flat. So that's f of x is equal to 0, which is a flat line. And now I'm going to slowly start adding all the other terms. So of course, if a0, okay, this is just to show you. So if a0 now all of a sudden shifts, right? So if it's positive, so notice it's just still a flat line. And it just goes up and down depending if it's positive or negative. So that's something that we have. Now, if I'm going to start making the higher order, so what's going to happen if I make a1 to be some number? Well, you can think back that that's going to turn this into a line now, right? Because it's going to be a1x plus a0. And indeed, if I start moving this around, notice that, oh, that flat line now all of a sudden turns to be a line with a negative or a positive slope. So that's what we have right there. Now, if I start adding, okay, so if now I put a quadratic kind of component in there, so let's say a2, and I start adding that to this, well, now all of a sudden, so notice what I start seeing is that, oh, well, wait a minute, this starts looking like a parabola, okay, and that's exactly the case, right? So this is a negative, okay, so the parabola is looking down. Notice your range that you have. So there's a peak, we can find that peak within here, and then it's anything below it. But if I swing this and I make the a2 positive, so whatever it might be, then it's going to start opening upwards. And again, now I'm going to have a minimum, and the range is going to be anything above. Now, if I add a cubic term, so that a3 instead of 0, and now I start changing this around, okay, now you notice that, oh, wait a minute, what's happening here? This kind of starts looking like a cubic, right? And then depending on what your values are of that cubic, it's going to be opening up, okay, and down, because it is a cubic, especially as your values of x for the magnitude get bigger and bigger. And then your range here is the entire number line, so the entire y output. So that's what you would see here. Now, if I start adding a4, so now it's n is equal to 4. So now if I start playing around with that, now you will notice that you're going to go back to having a maximum or a minimum. So here's your, okay, so for instance, a4 is equal to 0.6. I have a minimum. Now it looks kind of funny there, right? It's not exactly like a nice, beautiful parabola anymore, but that's because we have all the other terms. It's not a power function anymore, right? It is actually a polynomial function. So I can swing this thing back and forth, right? Depending on what I want to do. I can make it even look very funny, okay? Like this, for instance, if a4 is equal to 0.1. But it still has some kind of a minimum, and then it goes anything above. And then if I make this negative, so notice that it's going to flip the opposite way. So it has a maximum now, and it's anything below. That's exactly what you see for the range. And I can continue. So now a to the 5, it should switch back. Okay, and if I do this, now notice all of a sudden, oh, now I have the entire range, right? So, and I can swing this even further, stretch it out, okay, or make it kind of reverse course, okay, in this direction. And that's what I encourage you as a student to do. You know, you have decimals. Write this out for yourself and start playing around so that you can see that indeed your ranges are exactly what we've talked about in this video. So I'm not going to go any further. I think this is more than enough for you, and especially it's meant for kind of grade 11 math. And for that grade 11 math, I wanted to give you some kind of a visual like this, and also tell you about the domain and range for any polynomial. All right, so you have that. All right, thanks for watching. We'll see you in a future video. Bye, everybody. Take care.